So the gravitational force, the normal force, the frictional force, and the tension. So the gravitational force. So gravitational force, as you know, it is the force exerted by an object on any other object. Right? It's not only the Earth on us, but any two objects that have definite masses can pull each other with a certain force called as the gravitational force. And it is most evident when the mass of the object is higher. So like if there are two people sitting close by, you still have a gravitational force between them, but since the masses are too small, it's not that effective. Right? So but when you consider a heavenly object and any other smaller object, you feel that difference, you feel that pull, the pull is much stronger. So the most general definition of a gravitational force is the force that a body exerts on the second body. And it is, when you consider the situations that we are going to deal with, it is mostly directed towards the ground. We are talking about the Earth and the object system. So the gravitational force is directed towards the ground, and it is given by the expression Fg is equal to mass times the gravitational acceleration, mg.
Okay, yeah.
Okay, so and this is another representation of the Newton's second law. It just says that the total force is equal to mass times the acceleration. Here the acceleration is the gravitational acceleration. That's all.
Okay.
And when I say weight of the object, what do you mean by weight of the object? I say the object weighs 10 newtons. What is that weight that you are talking about?
It's, when you say 10 newtons, it's the gravity. It's the force of gravity.
It is the force of gravity. Okay. So let's look into it in more detail. Okay. When I say weight, it is actually the magnitude of the net force that is required to prevent the body from falling freely. Imagine that you have a ball, okay, a basketball or something in your hand. Okay. If you just remove your hand, the object will fall down with a force of gravity, mg, right?
Yeah.
And if you have to prevent the object from falling, you will have to exert an equally opposite force in the upward direction.
Yeah.
Right? So the ball doesn't fall down because you are exerting an upward force that balances the gravitational force. So suppose the gravitational force on the object is 2 Newton, then you will have to apply an upward force of 2 Newton to prevent it from falling.
Yeah.
So you say that the weight of the ball is 2 Newton. That is how you say weight is equal to the gravitational force. So it is the force that you will have to apply in order to prevent the ball from falling. Likewise, if the gravitational force is 3 Newton, you say that the ball weighs 3 Newton, because 3 Newton is the upward force that you need to apply so as to prevent it from falling. So that's how the magnitude of the weight becomes equal to the magnitude of the gravitational force acting on the object.
Okay, can you go back to the slide about gravity real quick?
Yeah.
Okay, force. Okay, thanks. Okay, let me go back.
Let me know when
I think there's one more equation after this.
Yeah.
Wait, what is the second equation?
I have just replaced
weight
Fg with
okay,
mg. So that's how you get weight is equal to mg.
Yeah.
Okay. So now there are different ways in which you can measure weight. Alright. So you use, just to tell the balance, no, you find in shops, not now, but in olden days. Right. You have the object that is to be weighed placed on one of the arms and the slotted weights in the other arm. So you are trying to add in more weights so that both of them balance. Alright, so it is actually the gravitational weight that you are trying to balance, and that's how you are trying to find out the mass of the object as well. Yes?
Okay.
Yeah. So the gravitational, when the gravitational forces on both the arms are made equal, then you say that the mass on the left side is equal to the mass on the right side of the pan. Likewise, you also have a spring balance for measuring weight. So, you use this to measure weight for your luggages, no, in airports, like to find out the approximate weight of your luggages when you carry it in the airplane.
Can you say that again?
Yeah, when you go traveling, no, you will have to measure the weights of your luggages, right? So you use this kind of a spring balance to get an approximate weight of how much you are carrying. So it is again you're trying to balance the gravitational force. So when you place an object on the spring, or when you tie the object to the spring stretches by a certain amount. Alright, and you actually calibrate the scale such that the pointer shows the weights, not the distance moved, but the weight of the object. Alright, so I when I look into this, I in one case I'm trying to balance it by adding more weights. In one case, I'm just reading the scale to find out what is the weight.
Yeah.
The object is like hanging, or it's put vertically like this. When do such weight measurements give inaccurate results? Can there be any situations when the result weight is inaccurate? I use a weighing machine or a spring to find out the weight, but I get a wrong result. Is that possible?
It could be, yeah.
It could be?
Yeah, I think so. Because
it can give one is that
I mean, it depends on the fact, like the scale. Like if the scale itself is
let's leave out that option. If the scale itself is inherently damaged, or that's a problem, let it be. We don't include that. But is there any other situation wherein such weight measurements can lead to inaccurate results? See, I am weighing this doing this measurements just by staying stationary, right? I stay stationary. I use the spring balance or the equilibrium balance to find out the weight. Now, what if I am moving?
If you're moving?
If I'm moving and I do the weight measurement.
The scale should be like settled completely. It shouldn't be already having, like, it shouldn't already be swaying if you're moving.
Okay, now when I say movement, it can happen in two directions. You can move horizontally and measure, you can move vertically and measure. Okay, so when you try to move vertically, actually like moving in an escalator or a lift, you are moving vertically, no? So in that case, you are actually accelerating.
Okay.
Right? So when you are accelerating in the direction in which the weight is being measured, then such measurements will give inaccurate results. Right? If you are in a room or moving in a train, if you're moving horizontally, it's not going to make much difference. Alright, the weight measurement will be always correct. But since the spring is hanging vertically and you are also moving vertically, the forces, the net force along the vertical direction will be different, because there is a force that's accelerating you upward, and there is another force called the gravity that is decelerating you. Right? So in that case, the weight measurements will lead to inaccurate results. Okay, so when there is a vertical acceleration, the results will be inaccurate. If you are moving horizontally, that's not going to make any difference. So in an elevator, you will feel that weightlessness, right? That's why you, like, when you go up, you feel very heavy, and when you come down, you feel like light.
Yeah.
That's because if you take a weighing machine and see that in an escalator, you will see the difference, because you have forces acting, the accelerating force acting in two different directions. It's not only the gravity, but the acceleration produced by the lift itself. Alright, okay. So in a moving elevator, if you measure the weight, it would be different from the actual weight. Alright, so this kind of weight that is a different weight that is produced, you call it as an apparent weight.
Okay.
So the same you will notice when you use or you try to weigh the object underwater. So you have gravity pulling it downward, and the upward thrust, the buoyancy trying to push it upwards, isn't it?
Yeah.
Yeah. So in that case also, you will feel the object to be weightless.
Yeah.
An example would be you actually try to draw water from a well. When the bucket is within the water, you will not feel the bucket heavy. right? Because you have an upthrust force that is trying to push the object upward,
Yeah.
so it will not be heavy. Once the bucket comes out of the well, once it is mid-air, then you will feel the bucket heavy, right? So
Yeah.
whenever there is an accelerating force acting in the direction of the measurement, you will get an apparent weight which is much lower than the actual weight, much lower or higher depending on what direction the force is acting.
Yeah. Okay.
All right, fine. So that was about the gravitational force and the weight. Now coming to normal force. What is this normal force?
It's the force of normal, so it's opposite to the force of gravity.
Okay. So normal force is the force that is exerted by the surface on which the object rests. Okay, so just going back to
it's equal and opposite force. So that's the normal force. Normal force is the opposite force to gravity, right?
yeah, it's an opposite force to gravity, but not always. Okay, it depends on how the object is oriented. If it is a flat surface, what you say is correct. Normal force is equal to the gravity. But if the object is inclined, then the normal force will not be exactly equal to the total gravitational force. There the situation will be different. We look into that. Okay. Now, whenever an object is at rest, it means that all forces acting on it are balanced, isn't it?
Yeah.
So since this object is at rest on the table, it means that the forces acting on the object are at rest, are balanced. So it means that it's not only the gravitational force. If you take only the gravitational force, then the object has to come down. So the gravity is just being opposed or counterbalanced by an force that's exerted on the book from the table. Only then the book can be stationary, right? If the book is acted upon only by the gravitational force, it has to come down, whatever is the situation. All right. Since it's not coming down, it's meaning that there is an opposing force, isn't it? This opposing force comes from the table. The table pushes against the book, exerting an equal force that is equal to the gravitational force, and you call that as the normal force. And remember that normal force is always perpendicular to the surface. Whatever direction the gravity is, that's not a matter of concern. If in this case both are parallel and anti-parallel. If suppose you have an inclined surface, this is the horizontal and this is the inclined surface, you have an object like this, how will the gravity and normal force be directed?
To the top left.
Top left. Gravity will always act vertically down. Whatever the orientation of the object, gravity will be vertically down. There is no inclination for gravity. Okay. So the weight or the gravitational force will act exactly down, but the normal force will be normal to the surface. It will be at right angles to the surface. This angle would be 90 degrees. Okay.
Yeah.
So in this case, the normal force is not
perpendicular to the surface. Okay. Yeah. That's what I'm trying to say.
So in this case, the normal force is not balanced by the gravity. You see, normal force is at some angle and gravity is at vertically downwards, isn't it?
Yeah.
So there is almost, if I just draw an imaginary line, this would be the angle between normal force and the gravity. So in that case, I cannot say normal force is equal to gravity, right? Normal force would be, so when we do that, I'll explain. So normal force is, you cannot always correlate normal force to gravity. That's what I wanted to impress. Normal force is the opposing force that the object experiences from the surface on which it is placed. And this normal force will be always perpendicular to the surface. So when a body presses against the surface will deform and it will push the body with a normal force Fn that is perpendicular to the surface. So however small the force is, however small the object is, there will be a seemingly small deformation that is happening. Maybe it is not visible to our eyes, but it happens. However, the rigid the surface is, that there is a force.
Okay.
So for a flat surface, the normal force and the gravity are pointed along these directions, and they actually balance. Now, the third type of force is the frictional force. The gravity.
Can
the
you
non-
go back to that last slide real quickly? That you.
yeah.
Alright, cool. Thanks.
Okay. So the third kind of force is the frictional force. What is meant by the frictional force?
So if the force of applied is being applied in one direction, the force of friction is the force applied in the opposite direction.
So it is the opposing force that opposes the motion of the object, right?
Yeah.
So if you take this example, there is a person pulling a box with a certain force. So you have an applied force that's acting like this. Equivalently, you have a friction that opposes the motion. So the motion is resisted by a bonding between the body and the surface on which it rests. So this opposing force is called as the frictional force or simply friction, and it is denoted by the symbol small f. Conventional symbol used for friction is the lowercase f. Okay, and it is always directed opposite to the direction of the intended motion, as we know. And the fourth, can we move on? You want to take this?
Oh yeah, sorry. Yeah.
Okay. And the fourth type of force is called as the tension. What do you understand by the term tension?
It's like potential energy, that tension. Like usually when I think of tension, I think of rubber band, and like the elasticity is allowing us to store some energy. So it's like the pulling force.
Okay. I think you have gone too much into that. Tension is basically when you have something tied to a rope or a string.
Yeah.
Okay. So that force that acts along the string is called as the tension force. So you imagine a weight is being hung from the ceiling. So this rope would be under the action of the gravitational force, the weight of the object, right? So this rope would be in a tensed state. It would be like stretched out.
Yeah.
So this force is called as the tension force, and it is always directed away from the body. So important thing is to know what is the force and how is its direction. So normal force is directed perpendicular to the body. Gravitational force is acting downwards. The third one was the frictional force acting opposite to the direction of motion, and the tension force always directed away from the body. Okay, and it's along the cord joining the object, and this force is called as the tension force because always the cord that is connecting the object to the ceiling or other object is said to be in a state of tension. Now if you have two things like this, you have one object and another object or some hand that's pulling against this, you have tension on the string. So if you consider if you are dealing with the object alone, the tension force has to be always directed away from the object. If you are considering the hand as your object, again the tension force is directed away from the object. Alright?
Yeah.
So it depends on what is the object under consideration. Okay, so since this I say because when you solve problems, there will be more than one object in the scenario. You will have to focus on what is the object that you are dealing with and then try to draw the free body diagram. So whenever you draw the free body diagram, you have to draw the tension force as directed away from the object.
Okay.
So this is another situation where the cord is under tension. You are trying to pull the object through a pulley. So if you consider the object or the mass or the block, tension is like this. If you consider the hand, the tension is like this.
Okay.
So always the tension force is directed away from the object. And one more assumption is, in all such situations where the tension force is involved, where a cord or a string is used, the underlying assumption is that the cord is massless, meaning the cord is not going to take part in this force calculation. Okay, when you try to draw the free body diagram, you are going to ignore the cord.
Yeah, I see what you're saying.
Yeah. Sorry?
No, I get what you're saying.
Yeah. Okay. You're not going to consider the cord at all. It's negligible. It has negligible mass, and it is not stretching. It's not a spring. That is what it is meant. Okay.
Yeah.
All right. So basically all these topics that we are doing is to try to use the free body diagram to solve the given problem. Okay, whether it is to find out the acceleration, to find out mass or force, whatever it is, try to understand the forces, try to draw the free body diagram and find out what is the like required quantity that is asked. Okay, so here is one situation which is involving tension. You have 4 objects A, B, C and D that is like hung like this and connected to the wall. Okay, so the longer top cord loops over a frictionless pulley and pulls with a force 98 Newton on the wall to which it is attached.
Yeah.
Okay, so this is 98 Newton and the 3 tension values are given. You are asked to find out what is the mass of all these discs.
Okay.
So how do we solve this problem?
What are the masses of the disc A?
So
the force of magnitude.
We'll start with one of the force. I'll just give you a hint. Okay. So starting with object A, my point is to draw the free body diagram. This is object A. What are all the forces acting on A?
So we have force of tension, which is going upwards.
When I take one of the tensional force is 98 Newton acting upwards. Then you have the tension between A and B. Okay, T1 is the tension between A and B, right? So how is T1 directed with respect to A? Is it upwards or downwards?
With respect to A, it's also upwards?
No. I told you tension will be always directed away from the object under consideration. I am considering the object A. So T1 will be always directed away from the object. Okay. And I also have the weight of the object acting.
Yeah.
Force of gravity acting on the object A. So now can you set up the Newton's equation for this condition? You have 3 forces acting. Write down Newton's equation. Newton's equation says that the net force has to be the mass times the acceleration.
Okay.
Okay. So what is the net force on A?
1 second. Wait. What was the equation again?
F net is equal to mass times the acceleration.
Okay. Okay, so we know that T1 is equal to 58.8 newtons, right? So it's...
So I'm just writing it step by step. F net is the total force, which is 98 minus T1 minus Fg. Okay? That's the total force equal to mass times the acceleration. It says that, does it say that the object is moving? Or what is the arrangement?
No, it's not moving.
It's not moving. So meaning it's 0. Right?
Yeah.
So now tell me what is the mass of the object. So I can rewrite this as 98 minus the tension is 58.8 minus mass of A times the gravitational acceleration is equal to 0. Right?
And we're trying to find the mass.
So I can find out MA from this. So
it's
MA
98 minus 58, right?
Yeah.
98 minus 58. It's 39.2.
Divided by the gravitational acceleration. So how much is it?
Wait, the gravitational acceleration is always 9.8?
Yeah.
Okay.
4 kgs. So mass of the block A is 4 kg.
One second, let me write this down.
So always remember to write the Newton's equation. That is how we have to solve it. That is the systematic way of doing. Okay.
Newton's equation. So it's F net equals mass acceleration. So then water really quickly. 1 second.
Yeah.
Okay. How?
Yeah. So that's how we find out mass of A. Okay.
Okay.
Now moving to find out the mass of the second object, B. Draw the free body diagram and set up the Newton's equation. Let me see how you can do that.
Okay,
Can you try?
Second object, which is
Yeah.
T2, right?
Yeah, second object is B.
Yeah.
Now look at the figure and tell me what are all the forces acting on B.
So you have the mass. Then you have the tensional force.
How many
And then
tensional
you-
forces?
What did you say?
How many tensional forces on B?
2.
2. So T1 has to be directed away from B. So this is T1. Okay.
Yeah.
And T2
And then you
again
have
directed away
T2.
from B.
Yeah.
And the mass of B. FG. I mean the weight of B. Sorry. Okay. So I'm not using too many subscripts. This Fg is for B. Okay.
Yeah.
So now set up the Newton's equation. F net is equal to ma. So add up all the tensions. T1 minus T2 minus Fg is equal to 0.
0.
So you can find out the mass from this equation. So
8. It's 49.
T1 is, what is T1? 58.8 minus T2 is 49 minus mass of B times the gravity is equal to 0. So mass of B is 58.8 minus 49 divided by 9.8.
Wait, let me get a calculator. 50.8 minus
1 kg.
Yes.
Now likewise compute it for C and D and tell me the answers.
Okay. Minus. Four
Yeah.
kgs.
4 kgs, fine.
Okay, then for the last one, it's wait, that was the last one, right?
No,
Wait.
last one is D.
T1, T2. Oh yeah, D. So I did A, B, C. Okay, so for D, we have draw the full body diagram. So, going up.
So D will have only just two forces, the tension,
I think I
T3,
did. Yeah,
9
which is
points.
9.8.
So it will be just 9.8 divided by the gravity.
9.8, which is 1.
1
Okay.
Fine?
Yeah.
Yeah. So the problems might appear different, but the logic is the same. Draw the free body diagram, identify the forces, use the Newton's equation. Fine?
Okay.
Can we move on?
Yeah. An 11 kg salami is supported by a cord that runs to a spring scale, which is supported by a cord hung from the ceiling. What is the reading on the scale, which is marked in SI weight units? So the reading should be the mass, correct? Which is marked so that this is a way to measure weight by time. Okay. So it's draw the force diagram. This is S, right? Again, the mass is 1. Okay. Wouldn't it just be 11?
See, you have the weight of the salami acting downwards, right?
Which is 11 kgs, right?
Weight
Force
is not
diagram.
11 kgs, Ashwath. Weight, the mass is 11 kgs. So weight has to be. This would be the tension on the spring, isn't it? Or whatever
Yeah.
is the spring reading. So this would be equal to Fg, which is mass times the gravity, and that's 11 times 9.8.
Wait, how is T equals to Fg?
It's not moving, no? It's just hung from the ceiling. The same logic that we used in the previous problem.
Yeah.
Mm.
Okay.
It's not moving, so what I did was T minus Fg is equal to 0. This is the Newton's equation. Net force minus, the net force is equal to gravity times mass times the acceleration. Since the right hand side is 0, I just compute the net force, so that's T minus Fg, so I get T is equal to Fg. And this is 107.8, no? 107.8.
Okay.
So let's move on to the next topic. What is that? Just 1 minute. Okay. never mind about the answers, just try to solve the problem. So it is basically about applying Newton's laws.
Yeah.
There are two horizontal forces on the 2 kg box in the overhead view, but only one is shown. Only the F1 is shown, right?
Yeah.
And the box moves along the x-axis. For each of the following values of acceleration, find the second force in unit vector
So the
notation.
force equal to it.
Unit vector notation. Yeah. You are given one of the force out of the two forces.
Yeah.
And
Which is 20 newtons.
yeah. So you have, and it's mentioned that the second force is also horizontal. Okay.
Correct.
So-
And then okay, I get it. So it just should be
Hmm.
10 meters per second.
So you set up the Newton's equation and you're given different values of acceleration. So Newton's equation tells me F net is equal to mass times the
Mass times
acceleration.
acceleration. So
F net is F1 plus F2. I'll write F2 so that if F2 is in the opposite direction, I'll get a negative sign for F2. Okay.
Yeah.
So algebraic sum is equal to mass is 2 times the acceleration is 10.
Yeah. So
Okay.
so 20.
20. So what is F2? F2 is 20 minus F1.
F1, which is 20, so 0.
0. So 20 minus 20, which is 0. So if the object is moving with a 10 meter per second square acceleration, the second force is 0.
0. There'll be
So-
no force. Okay,
that's
so then for B, F net equals mass times acceleration. So F, okay, so it's equal to F1 plus F2, which equals 20 plus F2 equals, wait, how did you find what F2 was?
Subtract MA minus F1. F1 plus
MA.
F2 is MA, no?
Oh, yeah.
So F2
So
would be
10
MA minus
10 minus 20.
How is it
Wait,
10
well,
minus
I don't
20?
get it. I don't get it. Mass.
See, the second acceleration is 20 meter per second square, not 10.
Oh, yeah, sorry. 20.
20 times 2 minus 20. So that's 40 minus 20, that's 20 newtons.
Wait, but why is it 20 times 2? Oh, because it's a 2 kg box.
Mm.
Okay. So 40 minus 20. So 20.
Mm.
So
Yeah,
40.
20. Okay?
Oh, yeah, and then subtract them. So it'd be 20. Yeah.
Yeah. So
So
now,
there's a 20 newtons force.
now acceleration, if the acceleration is 0, what does that mean? Before computing, you can just tell me. If the object has acted upon by two forces and results in a 0 acceleration, what is the second force?
Exactly opposite, the same.
Yeah, so the second force would be exactly the opposite of the first force, and that is minus 20 Newton.
Okay.
And the next part D is acceleration is minus 10, so it's decelerating actually.
Yeah, so that means that negative 10 divided by 2 is negative 20, negative 40,
So negative
negative
40
60,
newtons. Last one.
negative 40.
Negative-
And then
negative
Last
40.
one is negative.
Last one is negative 60. The same logic.
60.
Okay.
Yeah.
So it only says that when you have a 0 force, it's moving in the positive direction. A force of 20 Newton, again it's moving in the positive direction. When it's minus 20 Newton, that is exactly equal to the first force, then it stops moving. And when it is decelerating, minus 10 means it's decelerating or changing direction.
Yeah.
So when you apply a really high force, the second force is minus 40, the first force is just 20, so it is moving in the opposite direction, meaning it is decelerating.
Okay.
Alright, same thing. Yeah. Now, we learned how to solve the free body diagram for a horizontal surface. Okay. Now we'll learn a special case where the surface is inclined.
Okay.
So this is another scenario. For the horizontal surface, it is very trivial. You just have to identify the forces, find out the net force. Okay. Now in this inclined surface, you just have to use a small logic here to simplify the situation. All right. Okay. Can you read the question?
Yeah, and let the mass of the object be 8.5 kgs and the angle be 30 degrees. Find the tension in the cord and the normal force acting. Okay, so find the tension in the cord.
So the first point is to draw the free body diagram. So since this is an inclined surface, I'll just draw it on this. Identify all those forces acting here.
So you have the force of normal, you have the force of gravity.
Yeah. Normal force perpendicular to the surface, like this.
Yeah, and
Okay.
then gravity is going.
Gravity is vertically down.
Yeah. Okay.
And this is a frictionless surface, so you just
there's
have
no-
the tension like this. Okay. Now whenever
Wait,
we
if it's
draw
frictionless, why is there tension?
frictionless, meaning you don't have to consider the frictional force. That's all. A tension is there always on the cord. Otherwise, how does the block just rest there?
Oh, okay. I forgot it was a cord. Yeah, you're right.
Okay. There is a tension on the cord that's acting on the object. So these are the three forces. Okay. So now there are two ways to solve this problem. All right. Whenever we try to solve the problem, we try to align all the given forces along the x and y directions, isn't it? That is how we were
Okay.
always solving. So in this particular diagram, how many of the forces are acting along the conventional x and conventional y direction? Can you tell me? Conventional.
There's only one force that's going against the conventional y axis,
Yeah.
which is the force of gravity.
Yeah, this is the only force that's acting along the conventional y direction. The rest are all making inclined angles. Okay.
Yeah.
So if you draw the free body diagram, it will. I'll just draw the conventional x-axis axis using dots. Okay. So this is the conventional x-axis, and this is the conventional y-axis. So one of the force, that is the friction, is acting at an angle. Oh, sorry, the tension is acting at an angle theta. Okay.
Okay.
And mg is acting vertically downward, and the normal force is again inclined like this to the conventional axis. Okay, isn't it?
Okay.
So this angle will also be from the mathematical derivation. This angle will be again sorry, not mg, this will be theta. Sorry, this angle will again be theta. Okay.
Yeah.
Okay. Now, when you try to solve it, you have to split two of the forces along the conventional x. Only one is actually along the y direction. The other two are at inclined angle. So, you have to split two of them. So, I will have to make t cos theta this way and t sin theta this way. Right? T cos theta along the horizontal, t sin theta along the vertical. Likewise, for the normal force, this component would be n cos theta and this component would be n sin theta.
You're adding them, right?
Yeah. So I will have in total 5 components of the forces: n cos theta, n sin theta, t sin theta and t cos theta along with mg. So 5 forces. Okay. 3 along the x-axis, 2 along the x-axis and 3 along the y-axis. Am I right?
Yeah.
Yeah. So n sin theta and t cos theta along the x-axis. And what are all those on the y-axis? N cos theta, t sin theta and mg along the y-axis. Okay?
Yeah.
Okay. Now this way of solving will create a lot of problem, because out of the given forces, you have to split too many forces into their components. You have to fix N, you have to fix T, which are all at different angles from the conventional XY direction. Alright? Okay, so this is a tedious process. Alright, you can solve it this way, but this becomes tedious. Alright, so the easiest way to solve would be just to tilt your just change your perspective. Okay, just to tilt the conventional XY direction along the incline. Okay, now my XY is not any longer along the conventional direction. My inclined surface becomes my X direction, and the perpendicular to the incline becomes my Y direction.
Okay.
Now this will simplify the problem. Alright, now identify which are all the forces along the X and Y directions for the given object. Now I have just tilted the incline by an angle theta, tilted the conventional axis by an angle theta.
So, plus theta, T plus...
So I don't have any components for T. T is perfectly along the X-axis. Right?
Oh, yeah, okay.
Because I have assumed, or I have taken the new T as, the axis as the incline. So T is acting along the incline, so T is perfectly aligned along the X-axis, the new X-axis.
Alright.
Right? And the normal is perfectly aligned along the Y-axis.
So it will be
only the mg.
Minus theta.
It will be only mg that I have to split.
Yeah.
Since I am talking about motion along the incline, so this will simplify the things for me. Otherwise, I also have to take the displacement component along the, if you take the previous notation, I still have to find out the displacement along the incline and vertical to the incline. That will create a lot of problem. You can solve it. It's not that you cannot solve, but this would be the easiest way. Just if you tilt your perspective, you will simplify things. Okay?
Yeah, I get it.
Yeah, so now since this was theta, this angle will also be theta. Okay, from the law of just triangles and all, no? So this will become theta. Now this will have just two components, mg cos theta and mg sin theta. Okay, now I have just 4 forces, 2 along the x-axis and 2 along the y-axis. So tell me, what are the x forces? Forces along the x-axis? The new x-axis.
The force of gravity
x-axis.
Theta. Then you have the force of tension.
Mg sin theta and the tensional force. These are the 2 forces acting along the x-axis, new x-axis. Okay?
Yeah.
And along the new y-axis that I have found out, it is the normal force and the mg cos component of the gravity. Got it?
Yeah.
Yeah. So this way you will be able to simplify things. Now I can write the Newton's law for this component and this component. Since it's not moving along the new vertical, it's moving along only the new horizontal. The motion has to happen only along the incline. No, it cannot go perpendicular to the incline. So just find out what is the F net along the x-axis, and then we'll try to solve it. Alright?
Okay.
So solving we will do it later, but just telling you the procedure. So if I do it in a conventional method, it becomes tedious because I have to split too many forces into their components. And sin theta, cos theta, bringing all those things, it will create a lot of confusion. You can very well do if you are expert, okay, if you like master it.
Yeah.
But the easiest way is just let normal and tension be along the direction. Now let me tilt the x-axis and y-axis to align along the normal and the tension. So this will simplify, and I will need to only find out the components of mg, not of any other forces.
Okay.
Is that fine?
Yeah.
Alright, so I think I'll stop with this. Like when Athar joins, maybe we will try to solve this problem again. Okay, so you learned how to solve Newton's equation and draw the free body diagram for a horizontal surface. That is one specific set of problems. Okay, that is one specific situation. The other situation is when objects move along an incline. So when objects move along an incline, you are trying to change your axis itself along the incline, so as to simplify the forces. Alright?
Yeah. Yeah.
Okay. Can we wind up with this? So we'll do the continuation of this and more problems on the incline in the next class. Fine?
Okay.
Yeah. Thank you so much for joining. Bye. கிச்சுமா என்னடா பண்ற